Today we're going to be going through part 1 of 2 for the thermochemistry unit. This covers sections 12.1 to 12.17 in your CK12 online textbook. To start off with today, I wanted to go through a pre-assessment problem. So let's say that we have 2 pots of water which are boiling on a stove. They're both on the same setting. In pot A you have 500 milliliters and in pot B you have 1,000. So at this point I would ask you which one do you think would boil first, and I'm sure everybody would say the 500 milliliters would boil first. Based on common knowledge, you know that if you have less water, it's going to react, or in this case it's going to change phases a lot faster. The temperature at which both of these are going to boil is going to be 100 degrees Celsius. So this does not depend on how much stuff you have. This is what we would call an intensive property, whereas the amount of water for the boiling process, this would be extensive because the amount of water determines whether it's going to boil first or later. How does the amount of energy absorbed compare for each pot? If you have additional water, that means that you have additional intermolecular forces which need to be broken in order to separate the molecules from one another. So remember, inside of your pot of water, you have these water molecules which have their own covalent bonds, but there's also an attraction due to hydrogen bonding, which is really just a type of attractive force. It's not a real bond like ionic or covalent. So because you have more water molecules in here, it would take a lot more energy in order to separate them. Thermochemistry is the study of energy changes that occur during chemical reactions or phase transitions. So we're going to be talking about both chemical and physical changes here. When chemical reactions occur, the bonds are broken, and when new chemical bonds form, you either have an increase or decrease in the amount of energy which is present. So if there is less energy stored in the bonds in your final product, that means that energy is going to be given off. And if more energy is stored in those bonds, then energy must be taken in. Heat is the energy that is transferred from one substance to another. So this picture is in your picture template. If I have an object which is warmer than another object, if they come into contact with one another, heat is going to be transferred from the hot object to the cold object until they reach equilibrium, so until they are both at the same exact temperature. The law of conservation of energy states that in any physical or chemical process, energy is not created or destroyed. So this is similar to what Lavoisier was saying with the conservation of mass. So in our entire universe, energy is only transitioning from one form to another. Well, a way that you could think about this would be like with a light bulb. So you have electricity which is going into your light bulb, and what you really want the light bulb for is light. But some of that energy is not being emitted as light. If you have an older type of light bulb which is less efficient, you're going to also be losing quite a bit of energy due to heat. You know that a light bulb is going to get very hot if you have it on for a longer period of time. With newer LED type bulbs, they're more energy efficient because more of the energy which is being used is going towards the emission of the light that you want and not other things. In this unit, it's going to be very important that you're able to speak about these processes in a scientific way. System versus surroundings will help you to do so. So the system is whatever specific part of matter you're actually studying for an experiment, and the surroundings is everything in the universe outside of that which could potentially have an effect. If I have energy which is going into a system, into whatever I'm studying, this is an endothermic process. You might remember endo in terms of like endoskeleton inside your body. This means that heat is going inwards. Whereas in an exothermic process, heat would be going outwards. So the way that I would describe this using these two terms, I would say that energy is going from the surroundings into the system for an endothermic process, or from a system to the surroundings for an exothermic process. We'll talk more about these two words when we get into calorimetry. All right, with energy transfers. For an endothermic process, we have ice melting. Here you have your ice cube, and energy is going to be going into that ice cube in order to break the intermolecular forces, in order to get the water molecules away from one another. Same for evaporating. If I have a beaker of water, and then I add heat to that water, The energy which is being used to break the intermolecular forces makes this an endothermic process. Heat is going from the surroundings into the system. Both of these are kind of common sense, but exothermic might be a little bit harder for you to understand for water freezing and steam condensing. Let's say that I have a beaker of water and I put it out on a porch on a very cold day. Energy is always going from high energy to low energy, or in simple terms, from hot to cold. In that instance, your room temperature water is considered hot compared to the outside temperature, which is colder. So if the water is our focus, if the water is our system, I would say that water is going from my system to the surroundings. That makes it an exothermic process. Now, the reason why I say this is a little confusing is because sometimes students get stuck on the fact that exo is hot, which is not necessarily always the case. It doesn't have to be as hot as a flame. It just means that heat is being transferred from the system to some outside source. Steam condensing is the same idea. So if you're taking a hot shower, the steam is going to eventually condense on a cooler mirror. At that point, energy is being transferred from the hotter steam to the cooler mirror, and eventually, as energy is being transferred, it will no longer have enough energy to be in a gaseous state, and at that point it turns back into a liquid. For reactions within a cold pack, so this is one of the instant cold packs. I crack the seal between the two chemicals, they begin to mix together, and at that point, that cold pack needs additional energy to continue the reaction. So if I put my hand up against this cold pack, energy is going to be going from my hand into the cold pack. So since it's going into this system, that would be an endothermic process. Burning wood in combustion, that's basically common sense. You know that energy is coming out from those reactions. If you put your hand near a fire, you know that you can feel energy coming off of that. So next up, I have a picture of a bunch of different types of energy and how it can take different forms. Chemical energy would be like the energy which is stored within bonds. So for example, if you have something like methane, which is CH4, there are 4 carbon to hydrogen bonds here. When I burn the methane gas with the Bunsen burner, that energy can then be released in another form, in the form of light and heat. I'm not going to make you memorize all these types of energies, but they are here in case you want to see what other types you may have not thought about before. For example, gravitational or magnetic energy. Now in this unit, we're going to spend a lot of our time measuring energy. And we can measure heat energy in the form of calories or joules. Now I do want to be clear about what a science calorie is. So science calorie with a lowercase c, this is the amount of energy that it takes 1 gram of water to increase by 1 degree Celsius. So when I say that I have 200 calories, that really means that maybe I went up by 2 degrees Celsius for 100 grams. Now, when you think of calories, you probably think of food calories, which would be with a capital C. So you can see them in this label here. This food item is 25 calories per serving. 1 food calorie is actually equivalent to 1,000 science calories. And I know this is confusing. The only difference between these two words is the capitalization. A better way of thinking of this is that a food calorie is basically the same thing as a kilocalorie. So kilo being 10 to the 3rd power, or 1,000. Now, because of this confusion, I actually don't use calories too often in my class. I typically stick to joules, which is a better scientific standard. So here, I could say that 1 joule is the same as 0.2390 calories, or I could think of it the other way around and say that 1 calorie is equal to 4.184 joules. Now, theoretically, you could use this knowledge to convert from one unit to another. So let's say that I have 50 joules. I could then cancel out joules on my way to calories, and I have my equivalency right here. So 1 joule would be 0.2390 calories. Now, I wouldn't make you do this specifically on the quiz just for a conversion. We've spent a lot of time in conversions in this class between metric and stoichiometry. But there is a potential that you might have to convert from joules to calories at some point in the future. So this is how you would do it. All right, heat capacity is basically how good something is at absorbing heat before the temperature increases. So let's say that it is a hot summer day and I have 2 sets of lawn furniture. The set on the left is made out of metal. I know that the metal, when it's sitting out in the sun, is going to get hot a lot faster than other substances, like this wood chair over here. What I would say is that wood has a higher heat capacity. It's better able to absorb that heat before the temperature actually goes up. Metals traditionally have very low heat capacities, so it doesn't take a lot of energy in order to make a metal hot. This is the same reason why we use metals for frying pans and pots. Energy is transferred through them very efficiently, and it doesn't take a lot of energy to make them get hot. Specific heat capacity is for an individual substance, and these are standard values which you should be able to look up. So the heat capacity for water is 4.18 joules per gram degree Celsius. And as you can see, this number is a lot higher than other substances, especially metals. So this is a measure of how good something is at absorbing energy before the temperature would increase. The units here are joules over grams degrees Celsius, so you should have all three of them here. You could also see these values represented in calories, but like I said, we're not really going to use calories very often in this class. For the symbol, you could see the symbol as either C, CP, or C of different substances. I often write CW when I'm talking about the specific heat capacity of water. You could also see C of aluminum, C of iron, or in general, sometimes I write CM for C of metal, since we talk about metals a lot. Now that we know what specific heat capacity is, now we can use this to calculate our heat. So with our equation here, Q equals mc delta T, or in this case, Cm delta T, your Q refers to the heat of your reaction, C is the specific heat for your individual substance, M is your mass, and T is your delta T is your temperature change. Now it's very important to make sure that when you're finding your temperature change, you always do the final temperature minus the initial temperature. The sign here is actually going to matter, so if you have that backwards, you're not going to end up with the right answer. Alright, so for this equation, we're going to write out Q equals mc delta T. And then we're going to pull each of our letters from the word equation just like we would for gas laws. The Q here we are given, so it says that we have 134 joules. We have a mass of 15.0 grams. Our temperature change here is 62.7 minus 24, which is 38.7 degrees Celsius. And we're trying to find C. That means that we need to move our letters around to solve for C. So I'm going to divide both sides by M and delta T. That leaves us with C equals Q over M delta T. And when I plug in my numbers, I have 134 joules over 15.0 grams times 38.7 degrees Celsius. You divide by 15 and you divide by the 38.7 and you get 0.231. For the units, nothing cancels out here. So I'm left with units of joules over grams degrees Celsius. And that's what you should expect for a value of C. Specific heat capacity always has those units. For our next problem, we're going to be using the same equation. We're still using Q equals mc delta T. But this time I'm trying to calculate the heat energy. So Q is going to be my question mark. The mass is 15 grams, and my specific heat is unknown this time. Or sorry, actually my specific heat is kind of unknown. We will find it in a moment. And delta T, it says that we're going from 35 to 285. So that would be final minus initial being 255 degrees Celsius. Now I said that C is kind of unknown. It's not given to us up here, but they do give us a hint as to what it is. It does say that we have aluminum. And if you look at the data table over here, aluminum in joules per gram degrees Celsius is 0.90. So this is an instance where on your quiz, maybe I give you a data table and you can pull specific heat capacities for your individual substance from there. I'm plugging into my equation of Q equals mc delta T. It is actually already solved for the letter that I'm looking for. So I have 15 grams times 0.90 joules per gram degree Celsius. And then that's times my 255 degrees Celsius. The Celsius and the grams cancel out here. And I'm left with the value of Q of 3400 joules after I round for two significant figures. So that would be my final answer. Enthalpy is closely related to what we were just doing. The enthalpy is the heat content of a system at constant pressure. So as long as you're at constant pressure, our change in enthalpy of delta H will be the same thing as our Q value. The enthalpy is determined by the energy needed to break bonds versus the energy needed to make new bonds. And it can be represented in a picture form like what we have over here. So I wouldn't necessarily make you draw a picture like this on your quiz. I could, but I probably wouldn't. I would more likely ask you to interpret a picture like this, and then you have to explain what everything means and what's happening. In this example, we have methane, which is CH4 plus oxygen gas, and it's at a certain energy level here. I need energy to get this reaction going. I know that methane gas doesn't react spontaneously, but if I add a spark to it, this activation energy, then the chemical reaction can begin. The amount of energy that's stored in carbon dioxide and water is less than the amount of energy stored in methane and oxygen. So the line is lower down here, and I have this slope. The fact that I have less energy in the end than I did in the beginning in terms of the bonds means that energy must have been given off, or heat was evolved. This shows that this is an exothermic process. If this was an endothermic process, this line would be higher than the initial point. Calorimetry is where we're going to be using our Q equals MC delta T most of the time. A calorimeter is a device which is insulated, and it contains all of the heat transfers inside of it. Basically, instead of having the entire universe be our surroundings, it would just be the water which is inside of this cup. So if I have a chemical reaction going on inside of the water, I can calculate the heat of my surroundings, what's going on with the water, and then I can simply flip the sign to make it the heat of my reaction or the heat of my system. The reason why I'm allowed to just flip the sign for that, if I backtrack a little bit, way back here we talked about the law of conservation of energy. As long as heat is being conserved inside of my calorimeter, then I know that if the water absorbs a certain amount of energy, let's make up a number and say that is 2.5 kilojoules, well then something must have given off the same amount. So something else is going to have a negative 2.5 kilojoules. They always have to cancel out to be a net of zero, since energy is never created in the universe. It just comes from one form to another. All of the reactions that we're going to be doing with calorimetry are going to be aqueous, so they're all going to be occurring inside of water. So here we have a solid substance which is dissolving in water. If the temperature of the water increases as the reaction occurs, that means that heat must be released by the system in order for the temperature of the water to go up. This would be an example of, let's see here. So we have our water. We said that the temperature of the water is increasing, so that means that energy is going from the surroundings into the water, which is here. So if it's leaving the system, that would be an exothermic process. You should really think about this, maybe draw out a picture, try to visualize it, because it can be confusing. In terms of the water did absorb energy, so you might think endothermic at first, but you're always thinking of it in terms of the system. If water is going into the water, if energy is going into the water, which is the surroundings, that means it's going away from the system, so exothermic. All right, so with calorimetry, I mentioned that we're going to be using our Q equals MC delta T. What you would be doing most of the time is calculating the Q of your surroundings, or typically the Q of water first. And you do this by finding the mass of water, the specific heat of water, and temperature change of water. Specific heat of water is a constant. It's 4.184 joules per gram degree Celsius, so you would always use the same number for that. Temperature change of water you could easily find with the thermometer, and then your mass of water you would have to look up or get from the volume. Now, if I can find my Q of the water, based on the conservation of mass, all I have to do is flip the sign to make it Q of the system, or delta H. So let's take a look at this in action. I know that I'm going to be using the equation Q equals mc delta T here, so I have to figure out what I have. I'm trying to find Q, so that's going to be my unknown. I'm going to start with Q of water. And I need the mass of water, the specific heat of water, and the temperature change of the water. When I subtract the two water temperatures, I end up with a positive 7.0 degrees Celsius. The specific heat is 4.184 joules per gram degree Celsius. The mass of water in this problem is a little tricky. It says that I have 25 milliliters of 1 molar acid. What this really means is that I have 25 milliliters of water with a certain amount of moles of acid in there. So molarity stands for moles per liter. So I'm going to assume that these two are really just 25 milliliters each of water. I'm going to mix them together, and they had other stuff in them. They also had HCl and NaOH. So that means that I have 50.0 milliliters of water, and since the density is 1, multiplying by 1 gram per 1 milliliter, I get the same exact number, it's 50.0. So that's how many grams of water I have. So I'm going to plug that into my equation. So Q of W is equal to 50.0 grams times 4.184 joules per gram degree Celsius times a positive 7.0 degrees Celsius. That means that my Q of water is 1400 joules. All right, next. It says that I want this answer in kilojoules. To convert from joules to kilojoules, you can either do a one-step metric conversion, or you can simply divide by 1,000. So 1.4 kilojoules. All right, finally. It says that I actually want delta H, and delta H is really Q of the system, which is the negative of Q of the surroundings, or Q of water. So what I need to do here is flip the sign. So this is going to be a negative 1.4 kilojoules. And that would be my final answer. All right, for our next problem, we're trying to find the standard heat of reaction, which is represented by delta H with this little degree symbol here. The units here are going to be kilojoules per mole. Now, normally I would still use the Q equals mc delta T, but here I was actually already given my joules. So all I have to do is convert that to kilojoules. So 3,500 joules divided by 1,000, that's going to be 3.5 kilojoules. Now I also want moles. They don't give me moles, but they do say that I have 20.7 grams of sodium hydroxide. So I can do a one-step gram to mole conversion here. The molar mass of sodium hydroxide is 40.00. So when I divide these two, I end up with 0.518 moles. Now I'm going to take these two answers. If I want kilojoules per mole, and I have my kilojoules, and I have my moles, I'm simply going to divide these two to get my final answer. So I have 3.5 kilojoules. I'm going to divide by 0.518 moles. And when I divide those two, I get 6.8 kilojoules per mole. Now, most of the time when you're doing these types of problems, it won't be quite this simple. I would actually not give you the joules. You would have to calculate that first. So you would be doing the Q equals mc delta T part as well. And that's what we're going to do on the next problem. We're going to kind of bring everything together. So in this problem, we're starting off with 15.2 grams of potassium cyanide. It's dissolving in 52 grams of water in a calorimeter, and we have a temperature change. And we're supposed to calculate delta H for this process. We're going to be using the equation Q equals mc delta T. But to start off with, we're going to have to make sure that we're finding the Q of the water. So we're going to find all of the water numbers, and then we're going to convert it from there. So I'm going to pull out my variables from the word equation. And here it says that my mass is 52.0 grams. So this is one of the bigger mistakes that I tend to see students make. Plugging in the 15.2 grams instead, this is the mass of potassium cyanide. We're going to save that for the end, so we don't need that yet. So we have the mass of the water. The specific heat of water is not shown here, but it's 4.184 joules per gram degrees Celsius. That is our constant value for water. Our temperature change, we have 16.4 minus 27.1. That leaves me with a negative 10.7 degrees Celsius. So I plug all this in. I have 52.0 grams times the specific heat of 4.184 joules per gram degrees Celsius. We're multiplying by negative 10.7 degrees Celsius. Here, QW ends up being negative 2330 joules. Now, a few things for this. We know that our answer is supposed to be in kilojoules per mole, so I'm going to need to convert this to kilojoules. I simply divide by 1,000, and now I have my answer in kilojoules. Now next, what I actually found here was Q of W, which is not the same as delta H. Delta H is equal to Q of the system. And to go from water, which is the surroundings, to the system, I just have to flip the sign. So what this means is that if the water lost 2.33 kilojoules, lost because it's negative, that means the system must have gained the same exact amount of energy due to the law of conservation of energy. All right, now at this point we're halfway through the problem, and we're going to kind of hold on to this number for the end, but then there's this whole mole part. We need it to be in kilojoules per mole. So this is where we're going to take our 15.2 grams of KCN. We're going to cancel out grams to moles, and we get the grams from the periodic table. 65.12. This comes out to 0.233 moles. And this is my second answer. And these two together is what I'm going to use to find my kilojoules per mole. So this is where you kind of have to just use some common sense. If you want kilojoules over moles, then put your number for kilojoules over your number for moles. And then the units will be the way that you want them to be. This comes out to a positive 10.0 kilojoules over moles. All right, that concludes the first half of thermochemistry. In the second half, we're going to be working on thermochemical equations and also Hess's law.